interrupt me at any time if you need to ask any questions. If you do have a study in mind that you're preparing for, you may want to make some notes as we go through the different steps to help you prepare something. So I'll show you how to actually conduct a calculation at the end of the session. Okay, so there's 5 steps involved. The first thing you need to do is to specify your hypothesis. So what are you testing? What are your outcome variables? What is your intervention or your treatment, and what do you expect to see from it? So you have the null hypothesis, which is a H0, and the null hypothesis is if nothing happens. So if the treatment doesn't work, what happens? Well, if the treatments A and B are not different, then nothing happens, no change in the data. And your actual hypothesis or your alternative hypothesis is that yes, treatment A and B are different, so that there will be an effect of some sort. So if we were to look at some examples, if you're testing the effectiveness of a strength training program, so you've got one group of people compared to a control group, the group that's doing the intervention, the null hypothesis would be that the intervention does not work. So there's no statistical difference in maximal strength between pre and post-intervention testing. So you do 8 weeks of training, nothing changes. And the hypothesis is that there is a statistical difference in strength outcomes before and after the intervention. Another example is if you're testing 2 separate groups of people and let's say you're testing the effects of a treatment on heart rate. Null hypothesis, there's no difference in heart rates between A and B, and the hypothesis is there is a difference in heart rates between group A and group B. Third example, if we're testing 3 different drugs or 3 different groups of people, then again, there's no difference between A, B, and C, whereas the alternative hypothesis is there will be a difference. So maybe drug A works and drugs B and C don't work, for example. Okay, so that's the easy step. You know your study, you know what your aim is. What do you expect to see? What's your hypothesis? Okay, step 2 is you need to specify the significance level of the test. So this is where we talk about P. Some of you may be familiar with this, but maybe a recap on stats. P is the probability that your results occurred by chance. And we also call it the alpha level. So normally we set the alpha level at 0.05. And what that means is when you run, let's say you run a t-test or an ANOVA test or a chi-square, you get this p-value. If p is above 0.05, there is no statistical difference in your data. If p is below 0.05, you can say that your data is statistically significant. So let's say you do a t-test and you're comparing 2 different treatments. One treatment has an effect, one doesn't. And your p, if it does have an effect, would be lower than 0.05, which means that there is only a 5% probability that your data occurred by chance. That's what that means. So when you conduct a power calculation, you need to determine what is your alpha level. So what's the limit that you're giving to p, and just go with 0.05. That's the standard accepted value. This is a very good visualization. We'll get back to this in a minute, but just to give you an example, in this study, they looked at plasma estradiol levels after a triathlon. And we have males in black and females in white before the race, after the race, and this is the change between before and after. And what you see here is that males before the race had a certain level of estradiol in their blood. After the triathlon event, their estrogen levels went up. And there's a little star here, and that means that there's a significant difference between the 2 sets of data, between pre and post in this group of athletes. If you look at the females instead, if you just look at the mean, so just focus on the bar, you see the same trend, right? So females had a certain level of estradiol before the race, and then that level went up after the race. But there's no star. In fact, these researchers actually wrote NS, so no significant difference. So there is, even though the mean value does change and you can see a trend, there is no statistical difference between these 2. So there's no effect here. So there is an effect in males, there's no effect in females. That's what it's telling you. Okay. Any questions about P? So I'm not sure how familiar you are with the concept. Okay. Oh. Right, so step 3 is, this is where you need to specify the smallest effect size that is of scientific interest or of clinical importance for you. And this is probably the most difficult part of the entire power calculation. What this means is, if you do find a difference or if you find an effect in your treatment, what is that minimum amount of change that you would deem clinically significant or scientifically interesting? For example, if you're giving a treatment that supposedly affects heart rate, let's say you've got 2 groups of people. Group A has a heart rate of 180 and group B has a heart rate of 177. And let's say your P is lower than 0.05. So there is a significant difference, a statistically significant difference in your data between groups A and B. So your data is robust, there is an effect, but the difference is only in 3 beats per minute. So does that mean anything? Probably not. That's not going to have any effect on your patients if you're only changing their heartbeat by 3 points. So something that might be more meaningful, for example, could be one group having a heart rate of 180 and the other group has 170. So now you're reducing your heart rate by 10 beats, and that potentially has a clinical importance. So this is where you need to decide, okay, what is the minimum amount of effect that I would accept to say that, yes, the treatment works. Another example, apologies, these are all sports examples. A 12-week exercise intervention improves strength output by 5% compared to baseline. So if you get people to exercise for 12 weeks and after 12 weeks, all you get is an increase in 5% in their strength, is it worth putting all that work in for 3 months? Maybe not. So even if it's statistically significant, your treatment isn't, or your intervention isn't valid. So maybe you would expect a change in 15%, and then you'd say, okay, yes, it's worth all of that effort to get a 15% increase. Okay, so once you've decided your hypothesis and you say, yes, that I'm expecting to see a difference between treatment A and B or intervention A and B, then you have to decide what is the magnitude of that difference that you expect to see. How to decide this is very difficult, especially if you're testing out a new treatment. Sometimes it's quite easy in terms of mortality rates. You'd want to say, okay, what percentage do I want mortality rate to decrease? Ways to decide it, you can look at past literature on the subject. Even if the treatment or the drug is a completely new, there will be papers on maybe different treatments for the same disease, and you could look at, you know, what effect do other treatments have on that same outcome, and therefore what's a reasonable outcome to look out for. Or you could do some pilot testing. So normally, especially if you go for grants, you might have done some pilot testing on a smaller sample, and on that small sample you saw a change in X, and maybe that's what you're going for. So that's the number that you could stick into your power calculation. Okay, step 4 is to estimate the variance in your data. So when we talk about variance, we're talking about the spread of data. And I'm sure you've all seen the famous bell-shaped curve. If your data was normally distributed, you'd see something like this. So most of the values will be in the middle. And then you'd have a spread of some values are towards the higher percentiles and some values are towards the lower. So you could, if we said that this was IQ tests, for example, so most of the population will have an IQ of about 100 to 110. So most people fit in this frequency up here. So most people will have, let's say, between IQ of 90 and an IQ of 110. So they are all within this one standard deviation. Then you've got very few people that have an extremely high IQ and very few people that have an extremely low IQ. So when we say that there's a standard error, in this case, a standard deviation, you've got the mean and then a standard deviation of up to here and up to here. So this would be plus or minus, I don't know, let's say the population has an IQ of mean 100 plus or minus 10, so 110 and 190. And that one standard deviation will give you the spread of most of the data. So in terms of power calculations, you need to decide what's an acceptable or a predicted standard deviation that you'll see in your data. Again, this is not an easy thing to decide. If you have pilot data, that makes it a lot easier. So you can base your standard error on the pilot data that you've gathered. If you're basing it on previous literature, you can see, check previous publications and see what is the variance in the data that previous researchers have found. Again, if it's, let's say it's peak heart rate. So if you're doing a maximal, you're doing a CPET test, you're getting maximal heart rates, and based on experience or based on previous literature, you know that most people will have a peak heart rate somewhere around 188 plus or minus 5 beats. Roughly, that will give you most of the population. So you can use that to say, okay, I would accept a range of 5 beats or of 10 beats on my mean data. So either from piloting or from previously published data. One thing to keep in mind is that the larger the variance in your data, or the larger the variability in your sample, the more people you will need. So if you have, and we can play around with the numbers in a minute, I'll show you how that affects your power calculation. But if you have a homogeneous group, then your data will all be roughly within a certain parameter, and your standard deviation will not be very wide, because most of your patients or most of your participants will have roughly the same outcomes, and that makes it easier because the data looks the same. But if you have different genders, different ages, different fitness levels, different risk stratification, then that makes your sample very varied, and that's going to affect your data. So if that's the case, if you don't have a homogeneous sample and you're looking at a wider range of population, then you're going to need more people. So your standard deviation will be larger, and therefore you will need more people in order to account for that variance in the data and try to get a statistical significance in your calculations. Okay, so if we go back to this, this is the graph we were looking at earlier about estradiol before and after a triathlete event. And this is where standard deviation, it shows its effect on significance very well. So these little bars, these are what we call the error bars. And you can see that there's a mean value here, and the standard deviation will go plus or minus up to here. So that's the variance in the data in males, and plus or minus up to here. So they don't, let's say they don't really overlap. So it's pretty contained. In fact, we do have a significant difference in males before and after the triathlon in estradiol levels. In females, remember, we have a very similar trend. So it looks like estradiol levels increase in females, but look at the standard error bar, it's massive. And you can, I'm sure you can think about why this could be. There's all sorts of, they could be different ages at different stages in their menstrual cycles. That there could be some who may be in menopause or perimenopause, etc. So that would certainly be affecting the estradiol levels. And that is why there is no star, there is no significant difference, because the standard deviation is so massive that some women might have decreased in estradiol levels by looking at this chart. And some of them might have increased a lot, some of them might have decreased a lot. And that's why you don't get a significant difference. So this is why you want your standard error bars to be not too wide, essentially. Same thing here. These are, this is looking at testosterone levels during strength training. So strength training program, you can see that there's a very marked increase in testosterone levels after 15 days of strength training in this group. Same thing here, but there's no star, so there's no significant difference. And if you look at the range of the error bars, if you just look at it visually, you can see that they overlap. So there's people that were down here, the mean was from down here to up here, but some people were way up here and might have gone down here at the end. So you don't really know what's happening to the individuals. Okay. So hypothesis, minimal detectable change or clinical significance, then standard deviation. And then the last step is the intended power. This one's very easy. You normally go for 0.8. So the power of the test is the probability of finding a significance in your alternative hypothesis. And it's between 0 and 1. And you would want the probability to be somewhere around 0.8. If you're applying for a grant, sometimes you might want to go for a power of 0.9, just to show that you want to make sure that you get very robust data. A higher power will require more participants, but anything above 0.8 is considered to be strong power. So normally you're fine to go with 0.8. Okay, so recap, specify your hypothesis. For example, there is a difference in heart rates between groups A and B. Step 2, specify your significance level. Just go with 0.05 because that's what we always use in statistics. Step 3, specify your smallest acceptable change. So the clinical significance of your data. For example, if we're sticking to the heart rate example, you would want to see a difference in 10 beats between group A and B. Specify your standard error. So make sure it doesn't overlap. So another rule of thumb, normally, if in this example, if you've got 180 beats versus 170, you don't want a standard deviation of 30 because that means that you'd have a very wide range and you'd be overlapping the means. So in this case, you'd probably want a standard deviation of between 5 and 10 because it keeps the means contained within those two ranges. And then you want to specify your intended power, stick to 0.8. Once you've done that, you can do lots of fancy math and actually calculate it by hand, or you can go to this website, which gives you a different type of power calculation depending on the test that you envision. So I've put 3 examples here. They do have a lot more on the website, but let's say you're testing, let's say you're comparing 2 groups of people. Okay, so if we click on that link, that takes us to this calculator here. And we've got group A, so let's stick to that heart rate example. Let's say group A has a heart rate of 180 and group B has a heart rate of 170. My sampling ratio is the number of participants in group A divided by the number of participants in group B. So usually you stick to a 1-to-1 because you would want to have the same number of participants in each. Standard deviation of 10, for example, in this case, calculate power is 0.8, as we said, and type 1 error, alpha or P is 0.05, so 5%. So in this case, with this information, here it tells me how many participants I need, and it tells me I need 16 participants in my group B. So I'll need 16 participants in group A and 16 participants in group B, so 32 in total. That's what that's telling me. And I can play around with these numbers. If I had a standard deviation of 5, you can see that the sample size goes down. So what I'm doing here is I'm saying, okay, if the variance in my data is very small, and actually I expect everybody in group A to have very similar heart rates, and same for group B, so a low standard deviation, then I don't need many participants to get a statistically significant result. Okay, but then again, that's not reality. So heart rate in particular, you will know is extremely variable between different people. So something that's probably more realistic is maybe a variance of 10. So there you go, get 16 participants. Another example, if we did a paired t-test, so we're testing one group of people under 2 separate conditions. The calculation looks like this. So we've got power, expected power is 0.8, alpha is 5. And this is where we have the null hypothesis versus our alternative hypothesis. So let's say we're doing a CPET test, and we expect to see a VO2 max of 35 at baseline. And let's say that I give them an intervention of 8 weeks of training. After 8 weeks of training, I would expect to see an increase in their VO2 max, which is the amount of oxygen utilization. I'd want to see that increase to 40, from 35 to 40, right? So this is my null hypothesis is nothing changes. So 35 remains 35 after 8 weeks. And my true mean is, okay, well, after 8 weeks, it went up to 40. And for VO2 max, based on experience, based on previous literature, I'd expect a variance of maybe, let's say 5, depending on how homogeneous my group is. And here it tells me I need a sample size of 8 people to get this type of data. If I get a bigger change, I can play around with the numbers again. So if I get a massive change, I only need 1 person, which is, that's a bit unrealistic. Let's say we increase our standard deviation to 15 for that amount of change. So as my standard deviation went up, you can see that my sample size also goes up. Okay. If I see a very small change, so let's say we get a change, but it's not clinically significant. So from 35 to 36, then it tells me I need 1,700 people, because that's just not going to happen. And because the standard deviation is so big that it's overlapping between the two means. So if I reduce the standard deviation to 3, my number goes down to 71. So you can see how you can play around with the numbers. There is no right or wrong way to do this. This is completely up to the researcher to determine what's an appropriate number, what's an appropriate change to determine between the two groups, what's an appropriate variance in the data. And that will really depend on how homogeneous your sample is. That's something you need to consider. So if you are, again, if you're only testing postmenopausal women, then you'll have a very homogeneous group, and you'll know that there won't be a lot of standard deviation, a lot of variance in your data. But if you're testing a range of populations, then standard deviation will go up. Last example, if you're comparing more than 2 groups of people, so let's say we're comparing 3 different groups of people or 3 different treatments, you got a very similar setup. So you pick 2 groups, group A and group B, and a standard deviation, and then you have number of pairwise comparisons. So how many times are you testing these people? How many different groups do you have, or how many different treatments do you have? So let's say we have 3 different treatments, calculate that, and it gives you a number. If you scroll down on this website, it gives you an explanation as well on each of the tests. And here on the left-hand side, you have all the different tests. So testing proportions, comparing proportions, comparing paired proportions, et cetera, comparing K proportions. That's the one we just did now. Odds ratio as well for anyone using ratio data. Okay, I hope that was helpful.